The last time, we started off by analyzing medium transmission lines using end condenser method. The way the phasor diagram was derived when looking at the equivalent circuit diagram of the line was looked at. In the same vein too, the formula obtained when analyzing the phasor diagram was used at the end to calculate the sending end current, the sending end voltage, the line regulation, and the supply end power factor. All these were obtained using the formula that was derived from the phasor diagram. In today's series, we will continue to analyze medium transmission using nominal T method. So without any further ado, let's get started.
Before we begin to start analyzing medium transmission lines using nominal T method, it is important for us to restate the characteristics of medium transmission lines again. Medium transmission line is a line with an effective length of between 80 km to 150 km, and with a line voltage that is as high as between 69 kV to 100 kV. Lines with these parameters are usually considered as medium transmission lines. Another thing worth noting is that because of the length of the transmission lines, there is sure going to be capacitance buildup within the overall span of the transmission lines. So the capacitance of the line is usually uniformly distributed over the entire length of the line. But yet, reasonable accuracy is obtained by considering the capacitance of such a line lumped at one or more places.
So, what we did in the previous series was to lump the capacitance just before the load. But just that when using that method, there are some limitations that come with using end condenser method. When using this method, there is a considerable error of about 10% in the calculations. So the effects of the line capacitance are overestimated using that method. However, when we analyze a medium transmission line using nominal T method instead, the whole shunt capacitance of the line is assumed to be lumped at the middle of the line. With these, the impedance is halved in such a way that the line resistance and reactance are assumed to be lumped at either side of the shunt capacitance.
So the equivalent circuit diagram will be drawn like this. Here, the capacitance of the line is localized at the middle in such a way that impedances are at the either side of the capacitance in the middle. So in order for us to have an estimate of the impedance at either side, then we will need to divide the impedances of each side by 2. This will be understood in just a moment. Now the impedances will be denoted Z over 2. That said, we can analyze our circuit. So Vs is the sending end voltage, Is, on the other hand, is the sending end current. On the sending end side, the resistance of the impedance will be R all over 2, while the inductance of the impedance will be X all over 2. Now the current coming from the sending end, Is, which has flown through the impedance at the sending end, will now split into 2 in such a way that the current will flow to the capacitance and the receiving end respectively. So the resistance of the impedance will be R all over 2, while the inductance of the impedance will be X all over 2, respectively. While Vc is the capacitance voltage, Ic is the current flowing through the capacitor. Now, at the receiving end of the load, Vr is the receiving end voltage of the load, while Ir is the receiving end current at the load, respectively. With all these here, we have been able to form an ideal nominal T circuit.
Now that we have an equivalent circuit there, a phasor diagram can be drawn while making reference to that diagram there. So because we are considering the behavior of the line at the receiving end there, VR will be made as the reference of the phasor diagram. Again, because the load that is usually connected to electrical lines are mostly inductive load by nature, the current IR received at the transmitting end will lag behind the voltage by 90 degrees. With these, IR will be drawn here. However, we know that the current flowing through a capacitor is usually leading by 90 degrees. With these, IC will be drawn here, so we can shift IC here. To get IS, we can make reference to Kirchhoff's current law here. We all know that this states that the algebraic sum of all the currents entering and exiting a node must equal 0. With this in mind, we can use it to work out how our circuit equation will be. That said, the resultant of the receiving end current IR and the current flowing through the capacitor IC will equal to the sending end current IS. Also, in order to get the phasor diagram of VC, we will need to apply Kirchhoff's voltage law here. This also states that The total sum of all voltage changes in a closed-loop circuit is equal to 0. What this means in practice is that the electromotive force, which is also known as EMF, so when EMF is present in a circuit, this is equal to the total sum of the voltage drop across any form of the circuit component. And in our case here, the component that causes a drop in this circuit is the impedance. So when applied, the current received at the receiving end, IR, plus the value of the resistance, which is R all over 2, will lag by 90 degrees as drawn here, while the current flowing from the resistor IR will also passes through the inductance, which is X all over 2. We also know that current in inductance will be leading the voltage by 90 degrees. So the resultant of these parameters here is the value of the voltage present within the capacitor, Vc. Similarly, the same can be applied when analyzing the sending end voltage Vs. When we applied Kirchhoff's voltage law to this loop here, our equation will be the sending end current Is plus the value of the resistance all over 2. Of course, we know that this will also lag behind voltage by 90 degrees, while the current Is will also flow through the inductance also, which will be leading the voltage by 90 degrees. So the sending end current Is plus X all over 2. The result of both will be the sending end voltage Vs.
Now we can easily compute our equations while making reference to the phasor diagram. So for equation 1, the receiving end voltage VR bar will equal to VR at an angle of 0 degrees, equation 1. The receiving end current IR bar is equal to IR at an angle of minus theta R, which because the load connected to transmission lines are usually in inductive loads by nature, and that is equation 2. Again, just like you said earlier when you were analyzing the voltage within the capacitance, you use Kirchhoff's voltage law, which is basically voltage drop as a result of some components within the circuit. So the capacitance voltage Vc bar will equal to VR plus IR multiplied by the impedance all over 2, equation 3. Again, don't forget that impedance is equal to resistance R plus the imaginary Jx. This will be our fourth equation. Now, let's look at the current flowing through the capacitance IC. Again, it is also worth noting that IC will lead Vc by 90 degrees. IC bar will now equal to Vc all over minus Jxc, which will further be equal to Jvc all over omega c. The resultant of these will be J omega c Vc bar. Now IC will now be J2 pi Fc Vc bar. Equation 5. Let's look at the phasor diagram again. You can see that almost pretty much of the formula we need has been gotten, except for the sending end current Is and sending end voltage Vs. For the sending end current Is bar, using the phasor diagram, Is bar will equal to IR bar plus IC bar. Equation 6. For getting the formula for sending end voltage Vs, and looking at the phasor diagram, and when we apply Kirchhoff's current law, then sending end voltage Vs bar will equal to capacitance voltage Vc bar plus sending end current Is bar, and the impedance all over 2, equation 7. The transmission efficiency for the line can also be analyzed as the line power received all over the sending end line power. This will be further simplified as the voltage received per phase, current received per phase, and the angle all over the sending end voltage per phase, sending current per phase, and the angle. The resultant of this will be multiplied by 100. Finally, we can determine the voltage regulation since we have the parameter we need, that is the sending end voltage minus the receiving end voltage, all over the receiving end voltage multiplied by 100. However, using this method to calculate the line regulation is best suited to short transmission lines. However, using this means for medium and long transmission lines, the value gotten will not be accurate enough, hence the reason why we might need ABCD parameter to analyze our medium transmission lines instead. This will be looked at in the coming series.
With that proving up there, we can use it to solve the following problem here. For example, a 3-phase 50 Hz overhead transmission line 140 kilometers long has the following constants. Resistance per kilometer per phase is equal to 0.23 ohms. Also, inductive reactance per kilometer per phase is 0.38 ohms. Capacitive susceptance per kilometer per phase is equal to 0.043 multiplied by 10 raised to minus 4 Siemens. Now determine 1. The sending end current, 2. The sending end voltage, 3. The sending end power factor, and 4. Transmission efficiency when supplied with a balanced load of 3000 kilowatts at 132 kV of 0.8 lagging. Calculate using nominal T method.
Before we'll start, let's convert the current and voltage to phase. So the receiving end voltage will be 132,000 divided by root 3. The resultant of this arithmetic calculation will equal to 76,210 volts, while the receiving end current IR flowing through the circuit is equal to 30,000 times 10 raised to power 3 all over root 3, multiplied by 132 times 10 raised to power 3 multiplied by 0.8. The resultant of these will equal to 164 amperes.
Perfect. It is important that we note the following. The cosine angle at the receiving end is 0.8, and the cosine inverse of 0.8 is 36.86. That said, sine 36.86 is approximately 0.6. Again, we can also compute the value of the impedances. So 0.23 ohms times 140 is equal to 32.2 ohms. Similarly, the inductive reactance of the line is 0.38 multiplied by 140 is equal to 53.2. And finally, the susceptance of the line is 0.043 times 10 raised to power minus 4, all multiplied by 140. This will equal to 6 times 10 raised to power minus 4. So the impedance per phase is equal to Z bar equal to resistance R plus imaginary JXL, which is equal to 32 plus J53.2. Now when we look at our reference phasor, which is the receiving end voltage VR bar, this is equal to VR plus J, and because the angle it is at 0 degrees here, VR bar will equal to 76,210 at an angle of 0 degrees. In calculating the receiving end current, and when we consider the imaginary line, the receiving end current IR bar is equal to IR multiplied by cosine angle R minus sine angle R, which is 164 multiplied by 0.8 minus J.6. The receiving end current IR bar is equal to 131.2 minus J98.4.
Now let's calculate the voltage across the capacitor. Again, let's look at the phasor diagram and line equivalent circuit. Again, when we apply Kirchhoff's voltage law here, then we can use the following equations. This will be C1 multiplied by V1 bar, all equal to receiving end voltage VR bar, plus receiving end current IR bar, multiplied by impedance all over 2. When we slot our parameter here, we will have 76,210 plus open bracket 131.2 minus J98.4 close bracket multiplied by open bracket 16 plus J26.6 close bracket. Now the resultant of the above arithmetic will give us this. Now when we further simplify this here, our final value will be 80,926, 64 plus J15.52. So the charging current IC is equal to JYV1. This will equal to J6 times 10 raised to power minus 4 multiplied by this. Our charging current IC bar is equal to minus 1.149 plus J48.5.
Now that we have all the data we need, we should be able to calculate the sending end current IS. So we can start applying the formula we derived from the equivalent circuit of the line and the phasor diagram of the line. In our case here, we will be using equation 6. Again, don't forget that we applied Kirchhoff's current law here. So the sending end current IS bar will be equal to IR bar plus IC bar. IR is 131.2 minus J98.4 plus IC, which is minus 1.149 plus J48.5. The resultant of those two will be 130.05 minus J49.9. Now, in order to be able to get the rate at which the sending end current IS lags behind voltage, then there is a need to convert our answer to polar form. So when we convert from triangle to polar form, the sending end current IS bar will be 139.29 amperes at an angle of 20.9 degrees.
For the sending end voltage Vs, we will be using equation 7. Again, this is equal to the voltage across the capacitor V1 plus the sending end current IR multiplied by impedance all over 2, that is 80,926.64 plus J15.52 plus 130.051 minus J49.9 multiplied by 16 plus J26.6. The resultant of these will further be simplified, which will now equal to 84,334.796 plus J4576.47, but in order to get the angle of the voltage, we'll need to convert from triangle to polar form. This will now be 84,458.87, at an angle of 3.10 degrees. This can further be converted from phase voltage to line voltage, that is the phase voltage multiplied by root 3. This will equal to 146,287 volts.
In order for us to determine the sending end power factor, there is a need for us to add the sending current IS, which is 20.9 degrees, plus the sending end voltage Vs, which is 3.1 degrees together. That is theta 1 and theta 2. This will equal to 24 degrees. So cosine of 24 will equal to 0.91 lagging.
Subsequently, we can find the efficiency of the line, but before we can find it, there is a need for us to determine the receiving end power, and because we have all the value we need, we can just slot our value in. So the sending end power is 3 multiplied by the sending end voltage, Vs, multiplied by the sending end current Is, multiplied by the cosine angle at the sending end, that is 3 multiplied by 84,000. 458.87 multiplied by 139.29 multiplied by 0.91, this will equal to 32,116.473 kilowatts. Now, in order to calculate the efficiency of the line, we can say that 30,000 kilowatts all over 32,116.473 kilowatts multiplied by 100. The resultant of these will equal to 93.4%. And that is it for today's series. In the next series, we will be using another approach to solve a medium transmission line using the ABCD parameter. So until then, peace.